Let's look at problem 6 on the Winter 26 midterm 1 exam. There we are given a collection of 6 vectors, x1 through x6, which all live in R9. Additionally, we are told that the dimension of the span of these 6 vectors is 4. So what this means is that these 6 vectors span a 4-dimensional subspace of R9. So you should think of this as like a 4-dimensional slice of R9. The first question we are asked is whether these 6 vectors are linearly independent. The answer to that is no, they are not. The reason for that is in order for a collection of d vectors to be linearly independent, they need to span a d-dimensional subspace of whatever universe they live in. Okay? The issue is here we have 6 vectors, but they only span a 4-dimensional slice of the universe they live in. Okay? Which means I can remove 2 of these 6 vectors and still have the same span. Anything I could make with all 6, I could make with just 4 of them because the span only contains 4 different directions. So at least 2 of them are redundant, and this whole set is not linearly independent. Okay? That has some consequences, including into part B of the question, where we are given various ways to fill in this blank, and we are told to determine if each of those possible ways of filling in this blank are true or false. Okay? So let me read out the statement. There exists a vector b in R9 such that the number of ways to write b as a linear combination of these 6 vectors is blank. So the options for the blank were 0, exactly 1, exactly 2, or infinitely many. Okay? And so at first we are asked, does there exist a b such that there are 0 ways to make it using a linear combination of these 6 x's? And the answer to that is true. There does exist a b. There exists plenty, infinitely many b's that can't be made as a linear combination of these 6 vectors. Why is that? Well, these 6 vectors, they only span, or they only reach a 4-dimensional slice of all of R9. So anything that doesn't live on that 4-dimensional slice, which is infinitely many vectors, can't be made, no matter how hard we try, using a linear combination of x1 through x6. So that's why there are some b's that you can't make at all. Next question, or next possible way of filling in the blank. There exists a b such that there is exactly 1 way to make b as a linear combination of these vectors. Does there exist such a b? The answer to that is false. There are no b's that you can make exactly 1 way. And the reason for that, and we're going to talk about this more when we look at part C, is that when a collection of vectors is linearly dependent, then any of its linear combinations can be made in infinitely many ways. So if your building blocks are linearly dependent, then for any target you can create with the building blocks, you can always make it in infinitely many ways. This is in contrast to vectors that are linearly independent, where you can always only create any of its linear combinations in 1 way. The linear combinations of a linearly independent set of vectors are unique. But here, these vectors are not linearly independent, and so there don't exist any vectors that you can make exactly 1 way. If a vector is in the span of these 6 vectors, you can make it infinitely many ways. That also tells us why exactly 2 is not a possible answer here. There is no situation where there are exactly 2 ways to make a vector. Even if these things were linearly independent, then the answer to this piece, exactly 1 way, that would be true for the vectors in the span of these 6 vectors. But exactly 2 is never a possibility. Either you can make a vector in 1 way, or you can make it infinitely many ways, or you can't make it. Being able to make it 2 ways or 3 ways or any other finite number of ways other than 1 is just not a possibility. If you can make it more than 1 way, you can make it infinitely many ways. Which means, for the vectors that are in the span, it is true that there are an infinitely large many of ways that you can create them. Okay, so the ways that I would fill in these multiple choice bubbles are true, false, false, and true. Okay, what's going on in part C? In part C, we are given 2 different ways of expressing some vector b as a linear combination of our x's. So one way to make this vector b is by taking 4x1s minus 2x2s plus 6x3s. That's one way to do it. And another way to do it is by taking 3x1s, 3x3s, and from that subtracting an x5. And we are asked to find one other linear combination of the x's that gives us back b, okay? And as we just discussed, there are going to be infinitely many possible answers here, but let's look at some strategies for coming up with one of those answers while you're taking the exam. The general idea is that when your building blocks are linearly dependent, there is a non-trivial way to take a linear combination of them that gives you back the zero vector. And the general idea is, if you have a way of making the zero vector with your building blocks, well then just add that formula for the zero vector to either one of these equations, and you'll get a new equation where you have b on one side and a mixture of the x's on the other side. Here's what I mean. How could I make the zero vector using my building blocks, my x1 through x6? Well, one way to find the zero vector is just subtract these two equations, okay? If we subtract, what do we end up with? On the left, we're going to get a zero vector. And on the right, I'm going to get a 4x1 minus 3x1. That's going to give me an x1. How many x2s am I going to have? I'm still going to have negative 2 of them. How many x3s am I going to have? I'm not going to have negative 3 of them. How many x4s am I going to have? Still none. How many, did something wrong here. How many x3s do I have? Not negative 3. Rather, it's 6 minus 3, which is 3. How many x4s am I going to have? None. How many x5s am I going to have? Negative 1, so 1. And how many x6s? Still none. So now this is a linear combination of my building blocks that gives me the zero vector. So how do I find new linear combinations of these building blocks to get b? Well, I just add this formula for the zero vector to either one of these. Let's call these equations 1 and 2. If I call this equation 1, call this equation 3, if I do 1 plus 3, then on the left side, I'm just going to have b plus 0, which is still b. But on the right side, what am I going to have? I'm going to have 4x1 plus x1. That's going to be 5x1. How many x2s am I going to have? Negative 2 minus 2, so I'm going to have negative 4 x2s. How many x3s? 6 plus 3, that's 9. Not going to have any x4s or x6s, but x5s, I'm going to have 1. So that's a linear combination of my x's that equals b that is different from the original two linear combinations. How could I make another one? Well, I could take equation 3, that is this formula that gives me the zero vector, and add it to equation 2. All right, that would give me a different linear combination that would look like 4x1 minus 2x2 plus 6x3, and there would be no x5 component there. Actually, what I just read out, would give you the same as the first equation, okay, which makes sense because we got this by subtracting equation 1 minus equation 2. So if we added that delta back to equation 2, we would get back equation 1. So this is just one way you could do it because we took the delta and then added it back to the original thing. So that gives us a new linear combination than we originally had. So that's one way to do it. There's another way, okay? So 5, negative 4, 9, 0, 1, 0 is one way you could fill in the blanks. Another way you could do it is by averaging the coefficients. And this relates to a lab question that we once saw. But the way you get that is by, instead of subtracting, you add. So what if you do equation 1 plus equation 2? Well, then you have 2b equals, well, now you have 7 x1s. How many x2s you have? Minus 2. How many x3s you got? 9. x4s and x6s, still none. And then you subtract off an x5. Okay, all of this is equal to 2 b's, but we're just looking for 1 b. We don't need 2 of them. So how do I get there? Well, I just divide both sides by 2, and that gives you another linear combination. So I could fill in my blanks with 7 over 2, negative 1, 9 over 2, 0, negative a half, and then 0. Okay, and that's a different linear combination than the one we originally had written on the board just a moment ago. So again, that goes to show you, if there's one way to make a linear combination of a collection of dependent vectors, there are infinitely many ways. And just now on the board, I've written 4 different ways of making b using the x's, and there are infinitely many others. How could I think of others? Well, if we go back to what I had before, and I had the 0 vector equals some linear combination, ax1 plus cx2, whatever, I could multiply both sides of this equation by 2, or 3, or 17, or 344, whatever I want. Still going to have a 0 vector on the left, but I'll have different coefficients here on the right. And then if I add this new formula for the 0 vector to either one of these, well, that would give me another new equation. Okay, so that's how I would find new original ways of making B using my building blocks. And then lastly, we are told about 3 other subspaces. First, we're told that T is the span of x1, x2, and x3, and that U is the span of x4, x5, and x6. W, then, is the intersection of T and U. And we're asked for the range of possible values of the dimension of W. Okay, so there's a lot going on here. What do I mean by, well, first, let's make sure we understand what T and U are, okay? What is T? T is the set of all linear combinations of just the first 3 building blocks, x1 through x3. So the dimension of T is somewhere between 0 and 3. Okay, I mean, maybe the range is more restricted than that, because for it to be 0, then these would all have to be the 0 vector, but then I wouldn't be able to make a dimension 4 span out of all 6 of my building blocks, so it couldn't be 0. But T is some up to 3-dimensional subspace of R9, and similarly U is also some up to 3-dimensional subspace of R9. The intersection is the set of all vectors that can be made with x1, x2, and x3, or with x4, x5, and x6. The key to note here is that this intersection is not looking at all vectors that can be made using all 6 at the same time. That is not what the intersection is. Instead, that's the span of all 6 of them together, which is different, right? The intersection of these 2 spans, if you want to think about this geometrically, imagine this is T. It's the set of all things you can make with the first 3 vectors. And okay, this picture is going to be bad, but imagine I have another plane here that contains the set of all things I can make with x4, x5, and x6. Pretend that's U. These 2 planes, they intersect at a line. Okay, there's some better visuals in the notes for this. But that line contains all vectors you can make either with x1, x2, and x3, or with x4, x5, and x6. Okay, that's the intersection we're talking about here. And the question is, what is the range of possible values for the dimension of W? Well, we know that it can't be bigger than 3, right? Because the largest maybe possible value of the dimension of W is 3, and how would that happen? Well, that would happen if the dimension of T was 3, which is the biggest it could be, and the dimension of U was 3. So let me write down 3 as the biggest possible number, right? You can think of this as the case we're considering as being an overlapping Venn diagram where T and U are really the same set. All the way down to 0. 0 is the smallest possible dimension of the intersection. Okay, so these are the numbers I need to consider for my lowest and largest possible values. Now, it turns out 3 is not a possibility. You cannot, given the assumptions of this question, find a T and a U that have an intersection that is of dimension 3 while keeping this property still true, the dimension of the span of all 6 of them being 4. Why is that? Well, like I said, in order for the intersection of T and U to be of dimension 3, what that means is T and U need to be the same subspace, right? That is, the span of x1, x2, and x3 needs to be the same as the span of x4, x5, and x6. Because remember, there are only 3 linearly independent vectors here. At best, this can fill out a 3-dimensional subspace of R9. Same here, at best, this could fill out a 3-dimensional subspace of R9. But if their intersection is also a 3-dimensional subspace of R9, that just means T and U are the same 3-dimensional subspace. Okay, but what's the issue with that? If T and U were the same, well then, there are only 3 linearly independent directions, or total 3 linearly independent vectors in the set T intersect U. But if there are only 3 linearly independent vectors there, then the dimension of the span of x1 through x6 would be 3 and not 4. So because we are told the dimension of the span of all 6 of these vectors is 4, it can't be the case that t and u are the same subspace. Okay? Which means their intersection has to not be the entirety of both of them. Okay? And it means that given this assumption that the dimension of the span of x1 through x6 is 4, the dimension of the intersection of t and u cannot be 3. So the answer you would put in the largest possible value box is not 3, rather it's something smaller than 3. But what should the range be then? Is 2 possible? Is 1 possible? Is 0 possible? It turns out the dimension of w, that is the dimension of the intersection, could be 2, 1, or 0. And what I want to do is write out some examples that will hopefully help you think about how to visualize this when you see similar questions out in the wild. Okay, first I want to consider the case where their intersection is 0. That is, the dimension of their intersection is 0, which would mean their intersection is nothing but the 0 vector, which remember is in every subspace. Okay, what is one universe that can make that happen? Well, what if t is the span of these 3 vectors? 1, 0, 0, dot, 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 all those are zeros, comma, 0, 1, 0, and those are all zeros. And for this last one, why don't I put in 1, 1? 0, 0, 1, all of those are 0. Okay? What is the dimension of t here? It's 2, because there are 2 linearly independent vectors. In this example, again, I'm trying to come up with vectors x1 through x6, where the intersection of them, the intersection of their spans, rather, is just the 0 vector. But together, if you look at all 6 of them as building blocks, there are 4 linearly independent ones. Okay? How might I come up with an example of that? Well, I've already got 2 linearly independent vectors up here. What I need to do is come up with a set of 3 vectors, x4 through x6, where in total there are 2 linearly independent ones, because then 2 plus 2 equals 4, but also they are all linearly independent from the first 3. Okay, meaning you can't make any of these new ones using any of the first 3. Okay, that's what it means for their spans to intersect at the 0 vector. How might I make that? Well, here all I really activated were the first 2 components, right? Component 1, component 2. So a natural solution is just activate components 3 and 4, or the last 2 components, for example. So why don't I do 0, 0, 1, 0 and a bunch of zeros, 0, 0, 0, 1, and a bunch of zeros, and then 0, 0, 1, 1, and then a bunch of zeros. So now the last vector, like in the first case, is redundant with the first 2. That is, it is a linear combination of the first 2. But now what I have is a setting where in U, the 3 spanning vectors only have 2 linearly independent vectors amongst them, the first x4 and x5, but those linearly independent spanning vectors are linearly independent of everything in the first spanning set of x1, x2, and x3 as well. Okay? So now if I look at all 6 of these vectors, x1, x2, x3, x4, x5, and x6, if I look at all 6 of them, there are only 4 linearly independent ones there. 1, 2, 4, 5. These 2 can be made using linear combinations of the original 4. So that means the dimension of the span of all 6 of these together is indeed 4. But if I look at their overlap, well, there's nothing that I can make using these 2 building blocks and these 2 building blocks other than the 0 vector, right? Because if I look at these 2 building blocks, they only unlock vectors with non-zero components 1 and 2, and these 2 building blocks unlock all vectors with non-zero components 3 and 4. The only vector that has non-zero first and second components, or not non-zero, but it unlocks non-zero components, but they don't have to be non-zero because you can multiply by the coefficient 0 in your linear combination. The only vector that you can make of this form and of this form is the 0 vector. There's nothing else that can be written in this form and this form because of the placements of the zeros. So it is true that we've come up with an example where together the 6 vectors span a 4-dimensional subspace of R9, but the intersections of t and u, that is the span of the first three and the span of the second three, is just the zero vector. Nothing else can be made using a linear combination of these vectors and these vectors other than the zero vector. So indeed, this is possible. 0 is a possible answer, and so the lowest possible dimension of the subspace being the intersection of t and u here, is 0. So in that first box in the question, I would circle 0. Are 1 and 2 possible, or is 0 the only possibility? Well, I think it's a worthwhile exercise to come up with examples in these other cases as well. Why don't we look at the case of 1? Okay, why don't we look at a case where the intersection is a dimension 1 subspace? Remember, no matter what the dimension of the intersection is, I need to have 4 linearly independent vectors total. So this is really just a balancing act. Like, where do I put the linearly independent vectors? So, one idea is, why don't I put 2 linearly independent vectors in the first set and 2 linearly independent vectors in the second set, but one of those is overlapping. I'm trying to, I know what example I'm going to write down, but I'm trying to think through the thought process that I would follow if I were a student taking this on the exam. Why don't I start with the same vectors that I wrote before? And, I'm going to save some space here by not writing out span and then open parenthesis and then open curly bracket. Let's just write out the vectors. Why don't I start with 1, 0, 0, all the way down, and then 0, 1, 0, all the way down. That's 2 linearly independent vectors. And why don't I start with the same entire first set? So the third vector is the same x3 that I wrote in the 0 example. Now, why don't I copy 1, 0, 0, meaning now the intersection of these two sets, that is t and u, contains all scalar multiples of this vector 1, 0, 0, 0, 0. So it's a dimension 1 subspace of R9, as long as these other two vectors that I write down can't be made using any of these building blocks. So how would I avoid those building blocks? Well, I think what I could do is just pick something like 0, 0, 0, 1. Or, let's just make it super visually obvious in the video. Why don't I go with 0, 0, 1 at the very bottom? And this last vector, I don't know, we can make it some linear combination of these two, but why don't I just make it 0, 0, 0, 2, for example? Okay, let's check. How many linearly independent vectors do I have total here? 1, 2, that's redundant. That's redundant. 3, this is new. This is also redundant. So it turns out that I need to actually pick something different here. It can't be redundant with stuff I've already picked. So why don't I go 0, 0, 1, 0. Okay, and to clarify that this is different, we have a 0, 1 there. Now how many linearly independent vectors do I have? If I look at all 6 of them as a whole. 1, 2, copy of something, or not copy, but a linear combination of something, linear combination of something. 3, that's new. 4, that's new. I don't have the 8th and 9th components unlocked amongst the first 3. Okay, so total I have 4 linearly independent vectors, that's good. But if I look at their intersection, well, these two vectors move in a different direction than these two. Like I can't make this one using these two, and I can't make this one using these two, and I can't make this one using these two. But there is an overlap. The overlap comes in the direction of this first vector, 1, 0, 0, 0, 0, right? So if I were to graph these out, these two subspaces, the first of which has a dimension of 2, and the second of which has a dimension of 3, they overlap at a dimension 1 subspace. Okay? That means 1 is a possible answer also. My presentation of, or derivation of this example may have been a little messy, but make sure to pause the video here and understand where these 6 vectors came from. These two are linearly independent, and this third one is dependent on the first two, which is why if you look at the first 3, their span is a 2-dimensional subspace of R9. If I look at these second 3, their span is a 3-dimensional subspace of R9, because they are all linearly independent amongst each other. But if I look at all 6 of them together, There are only 1, 2, 3, 4 linearly independent ones, and the intersection of the span of these three and the span of these three is of dimension 1, because there's one linearly independent vector in that intersection. It's the one vector 1, 0, 0, 0, 0, 0, 0, 0. Okay, so 1 is a possible answer to the dimension of the subspace of W, or the dimension of the subspace W. And then finally, there's a question of, is 2 a possible answer? Could I find a case where the total number of linearly independent vectors is 4, but in the intersection, there are 2 linearly independent vectors? Okay, well, why don't I start with the example that has served me well so far. 1, 0, 0, so on and so forth. And then 0, 1, 0. Okay, and I want these two sets to have an intersection that is of dimension 2. So why don't I just copy these same two vectors, once again, zeros, and then 0, 1, 0. Okay, so these are the same two. How many linearly independent vectors do I have so far now? In total, 2. Right there, these two are independent, these two are independent, and if I look at all 4 together, still only have 2. So I think a solution to make sure that I get to 4 total is just put anything else here and here that are linearly independent to the 2 linearly independent directions I've already decided. So why don't I go 0, 0, all the way, put a 1 at the bottom, and then 0, 0, 1, 0. Okay, now in total I have 4 linearly independent vectors, 1, 2, 3, 4. But if I look at the intersection of the span of these 3 and the span of these 3, that would be a 2-dimensional subspace of R9, because there are 2 linearly independent vectors caught in that overlap. And that's this one and this one. So anything that can be made with just these 2 vectors exists in both T and U, but the span of these 2 vectors is a 2-dimensional subspace of R9. So 2 is a possible answer for the dimension of the intersection of T and U. Okay, this is a pretty tricky theoretical question, but make sure you're comfortable with how we arrived at the fact that the minimum possible dimension of W is 0, and the maximum possible dimension of W is 2. Make sure you're comfortable with that, and let us know, as usual, if you have any questions.